Last episode, Bayes updated a belief from one fact, but in practice, you don't get one fact, you get a sample and you have to guess the truth behind it. Imagine tasting soup. You don't drink the whole pot, one spoonful, stirred well, tells you the flavor. The pot is the population, the spoon is your sample, and the stir is what makes the spoonful representative. One spoonful can mislead, but take many spoonfuls and average. The more you take, the closer that average creeps to the true flavor. That's the law of large numbers, and it's why more data helps. Now repeat the whole tasting many times and look at the averages. They cluster into a bell whose width shrinks like 1 over root n, the central limit theorem. And to estimate the spread honestly, we divide by n minus 1, not n, to undo the bias. This is training. A mini batch gradient is a noisy but unbiased estimate of the true gradient. Bigger batches, less noise, by exactly that root n law. And bagging resamples the data to average away variance, the same averaging trick. Here's the whole thing in one file. We draw from a known population, watch the running mean converge, then build the sampling distribution of the mean, and check its spread against theory. Section 1 fixes a population, normal, with mean 5, sigma 2, and seeds the generator. Section 2 draws a stream and plots the running average, creeping toward 5. The law of large numbers, live. Section 3 takes 5,000 samples of size 30, averages each, and collects those means. Section 4 compares the spread of those means to the theoretical standard error, sigma over root 30. The printout proves both laws. The running mean lands right near 5, and the sample means cluster in a tight bell whose spread sits almost exactly on the theory, about 0.37 either way. The figure shows the convergence and the bell. That's how a sample becomes a trustworthy estimate. Next, how we tell a real effect from a fluke, hypothesis testing.